Hello everyone. Here we're going to look at topic 4 from exam 3, which is still integrating powers of secants and tangents. Last time we saw even powers of secants. This is case 2, integrating odd powers of tangents with secant any power. And so the importance of this topic is that secant does have to be present, because if you recall in case 1 where we dealt with even powers of secants, we had to have a secant squared to satisfy the du. But to satisfy the du in this situation, we have to have a secant present, because the derivative of tangent, the derivative of secant is secant tangent. So first we start with the basic example. This is one of the basic 6. You might recall the formula for the integral of secant of, let's say, kx. Tangent kx is going to be 1 over k times the secant of kx. That's our linear argument rule. So it does fit that form, so we can integrate that by inspection without a u substitution. We get 1/3, and then secant of 3x plus or constant. But then the question becomes, what if the power on tangent is higher than just the first power? And maybe there's a higher power of secant as well. Well, then we need a strategy. So here's a little cookbook recipe, once again, but the whole idea is reversing the u substitution process. In case 1, which was even secants, we isolated a secant squared because that was the derivative of tangent. In this case, our only choice is to isolate a secant tangent with the differential dx, because secant tangent is the derivative of secant. So then we're going to save that, and that's going to satisfy the du in the formula for the integral v to the n with respect to u. We'll convert the remaining factors of tangents to secants by the identity, and then we'll finish. So following this procedure, once again, note that the power on secant here is odd, so we cannot use case 1. Power on tangent is odd, and we do have a factor of secant present, so this case does apply. And so we borrow 1 factor of each. Taking away 1 factor from secant to the 7th, we're left with secant to the 6th. Taking away 1 factor from from tangent cubed, we're left with tangent squared of 2x. And those 2 factors that we borrowed, in that order of secant 2x, tangent 2x, we put with the differential dx, go so far as to box it off and write the word save. And I mentioned in that order of secant tangent because that is how we remember the formula for the derivative of secant. So at this point, you can look back at the cookbook recipe, and it says convert the tangents to secants by our identity. But the logical question you can ask would be, if our intent is for secant tangent to be the du in the formula for the integral of v to the n with respect to u, then whose derivative is secant tangent? And that, of course, is secant. So if we could change the remaining factors of tangents to secants, we will be able to start the u substitution process. And we can, because we have the identity that 1 plus tangent squared theta is secant squared theta. And so if our concern is for tangent squared, we isolate that. That becomes secant squared minus 1. So that's our next move. Recopy integral secant to the 6th of 2x, tangent squared, once again replaced by secant squared of 2x minus 1. And then we have the secant 2x, tangent 2x, along with the differential dx that's saved to satisfy our du. So we forced the du to exist in the form of secant tangent, changed everything else to be in terms of secants, which will be our choice of u. So u is secant of 2x. Okay, from here, hopefully it's routine. Du secant 2x, tangent 2x, oops, don't forget times 2, as well as the differential dx, and modifying, we have that 1/2 du is secant 2x, tangent 2x, times the differential dx. Now if we go back to the integral, we had chosen u to be secant, so here's u to the 6th, u squared minus 1, and the secant 2x tangent 2x that remains as we intended makes up 1/2 du. So making the change of variables, we have 1/2 integral u to the 6th, u squared minus 1, and the differential du. So at that point, before we can integrate, remember you have to have a sum or difference of terms of the form u to the n. So I'll recopy the 1/2 integral, distribute the u to the 6th, u to the 8th minus u to the 6th with respect to u. Now finally we can integrate. 1/2 integral u to the 8th integrates to u to the 9th over 9 minus u to the 6th integrates to u to the 7th over 7. Add our constant at that point. We'll distribute the 1/2 off to the side here. So 1/18th u to the 9th minus 1/14th u to the 7th plus our constant. And then remembering to write the little note mentioning what u was, and that was secant of 2x in this case. Okay, so we have another example. Tangent to the 5th, secant cubed. Doesn't matter about the size of the powers, just if they're odd or even. And I would probably suggest if it's an even secant, unless the power on tangent's really big, go with that method. But if secant's odd, as long as tangent is odd, then we can go with this odd power of tangent secant any method. So we're going to borrow one factor of each. So taking away one factor from tangent to the 5th, we're left with tangent to the 4th, 5x. Taking away one factor from secant cubed, we're left with secant squared of 5x. And we're going to push those factors over with the differential dx, but think about this just like we thought about it up here. Up here it was almost kind of natural that we wrote it as secant tangent because we borrowed it in that order. But in this example, it's kind of like the opposite order. But the factor of secant and tangent that we borrowed, we would like to express as secant 5x, tangent 5x. Because once again, that is the way we memorize the derivative of secant. So we're going to save that to represent the du, and then you can look back at the cookbook recipe if you like. But the logical question we could ask would be, if secant tangent's going to be the du, what's the trig function whose derivative gives us secant tangent? And that is secant. So therefore, if we could change the remaining factors of secant, or excuse me, the remaining factors of tangents to secants, then we'll be able to start the u substitution process. And we can because we have the identity. That 1 plus tangent squared is secant squared. Our interest is in tangent squared. So that would be secant squared minus 1. And as we've done in the past, if we need to tangent to the fourth, it's the same as saying tangent squared, quantity squared. So equivalent to secant squared minus 1 as a quantity squared. So that's our next move. And so tangent to the fourth. Okay, again, without even thinking about what we wrote over here, just try to think about it in your mind this way. Tangent squared is secant squared minus 1. So secant squared of 5x minus 1 will represent 2 factors of tangent to the fourth of 5x. To represent 4 factors, we're going to have to square that. And then we'll recopy the secant squared 5x and the secant 5x tangent 5x dx that we're satisfying for the du. And now we're ready for the u substitution, because we forced the du to exist in the form of secant tangent. We changed everything else to be in terms of the u that produces that du, in particular secant. So I'll kind of isolate this off to the side, so you know that was our side work. And now we're going to choose u to be the secant of 5x. So from here it should be pretty routine. Draw to secant, secant tangent, so secant 5x, tangent 5x. Don't forget the 5. And formally the differential dx as well. And so 1/5 du is secant 5x, tangent 5x dx. And now we go back to the integral. And we have u as secant, so here's u squared minus 1, but as a quantity squared, then times u squared, and then the secant 5x tangent 5x dx makes up 1/5 du. So all factors are accounted for. We're ready for the change of variables. Bring out the 1/5 integral. Then we have u squared minus 1 as a quantity squared times u squared and the differential du. So once again, we have to have a sum difference of terms that are of the form u to the n in order to integrate. And so therefore we have to expand this u squared minus 1 that's being squared. Since it's only being squared, you can take it off to the side and FOIL it out. U squared minus 1 times itself. And FOIL. But if you like to use the shortcut method, it's a nice method to have in your repertoire. Square the first, u squared squared, u to the fourth, twice the product, 2 times u squared times -1, minus 2u squared. Square the second, squaring -1, +1. Then we have times u squared, don't forget that, and the differential du. So foiling it out, you would get the same result, of course. Before we integrate, we're going to need to distribute this u squared. So 1/5 integral u to the 6th minus 2u to the 4th plus u squared. And now we can finally integrate. So I'll leave the 1/5, open up brackets. U to the 6th integrates to be u to the 7th over 7 minus 2 tags along. U to the 4th integrates to be u to the 5th over 5. And plus u squared integrates to be u cubed over 3. Add our constant. And distribute the 1/5. So 1/35 u to the 7th minus 2 over 25 u to the 5th plus 1/15 u cubed plus c, and again back substitute, write the note, and if you're writing the note, this is where u was secant of 5x. Okay, I've got 2 more examples for this lesson, but this has taken 16 or 17 minutes, so I think I'm going to stop there and have a part 2, because the video downloads are a little bit of an issue. So we'll see you in a few minutes whenever you decide to come back.